and we strap them on people, and we can still measure these motions and take a look. And that's what the data is plotted. The green data is the big fancy system. We call it the gold standard, looking at knee angles as you're walking. And then the blue is, basically a few $1,000 system. We hope to get that down to 100. If we made our own, well, very smart students that I have, they make their own. Hopefully that's hundreds or under $1,000. So orders of magnitude reduction in cost. And the great thing is you wear them and you go home and talk a little bit about some of our, again, our biomedical applications, so that now it becomes very interesting for different pathologies, locomotion pathologies. If the parents could be with their children, monitoring motion and things like that at a much more affordable kind of price. Okay, we're going to transition a little bit into spaceflight. Just one slide on a few definitions. I'll talk about the microgravity environment when you're floating, free floating in space, say up on the International Space Station, and some experiments we've flown up there. I'll probably talk a little bit about the moon. It's 1/6 gravity. We should definitely talk about Mars, because Odyssey just had opportunity, had a great landing. It's a great week to talk about Mars rovers, and we don't have humans there yet. That's 3/8 gravity. We'll call it a third. It's about a third. You never have to go on a diet on the moon or Mars. It's fantastic. Either way, 1/6 your weight or 1/3 your weight. So you're light, and you can all be marathon runners. I study astronauts inside the vehicle, so we call that intravehicular activities, IVA, and study astronauts outside in EVA, when they're in spacesuits, in extravehicular activity, EVA. They're only two acronyms I'll use. NASA has I kid you not, a blue book of acronyms. We have a big, thick book of acronyms from NASA, but those are the only two I'll use. As an engineer, but kind of a strange one, because I study people, not spacecraft, I just use engineering techniques to kind of look at sensory motor adaptation. So again, control theory dynamics, but I'm actually looking at human physiology and systems and movement. What do we study when we go into space? Well, we want to keep the astronauts healthy and alive, but it also tells us a lot about some things that are happening here on Earth. If you go up on a space station, you're going to probably lose 20 to 30% of your muscles atrophy, and you're going to lose about 40% muscle strength, and that's the good news. The bad news is you're probably going to lose 1 to 2% bone mineral density per month. Okay, now who wants to go on my 4-year Mars mission? Oh, wait, the younger students still want to go. But so what is that? So it's significant. So we want to counter, we call them countermeasures. We want to counter these deleterious physiological effects. If you look on the bottom right, that's a very high precision scan of a male, 37-year-old healthy male bone. If you look next, that's an unhealthy 84-year-old male with osteoporosis. I think you can see the structural difference in those bones. And we're worried about that. We're worried about that in the general population of aging, and we're worried about it for our astronauts when they get to Mars. Are they going to fracture? We haven't sent astronauts to Mars yet, so I do mostly human studies, but we do some animal studies on mice. The next two scans are looking at mice, because we can study them, and they're adults, so I'll show you that next. But a control study, and suffice it to say, I'll show you some data. A lot of bone loss, of course, in our Martian simulation. So, joke time. My life's goal is to not make our Martian astronauts look like that little squatty gentleman. So that's what his nurse is telling him. Okay. Well, as I said, it's hard to. It takes 10 years or so for me to fly an space experiment. So we do a lot of things in the lab here on Earth. This is actually underwater. And water tanks are pretty good simulation. We can't get rid of gravity, but I can load someone for 1/6. This is Mars. This is 3/8 your body weight. I'm loading through those black packages to get the right loading. Now we're flying in NASA's aircraft. It's actually known as the vomit comet. You fly up and you drop out of the sky, and you do it 40 times in a row. But we can truly get lunar, Mars, and microgravity parabolas. So on Earth, this is the only way we can truly get partial gravity environments. And we study, in this case, the locomotion. Just to show you a little data, this is data at 1G. I'm running left foot, right foot, and a normalized force trace. This is for the Mars simulation you just saw on that aircraft, and it's about half. So Mars is 3/8 loading level. but the forces I'm exerting on my body are about half, 1.5 compared to 3. Nothing's linear, especially with humans, but it's a reduced loading. That's the point, is the reason for the musculoskeletal loss in space is because we have very different loading profile. So that's the point of that. Here's to the, this is a little mouse experiment. He's running over a treadmill, he or she, I actually don't know, is running over a force platform, so we're measuring the forces. They're only 20 grams. People are much easier than mice, because you tell them to walk and run at a certain speed. You can't tell these guys much. But there they are. Here's the picture, if you will, of what happens where the loss is, the skeletal loss we see per month. We don't lose, actually we gain bone in our skull, so it's okay to call astronauts thick-skulled. Our arms, we don't lose any bone, but here's where we start losing bone. Down the spinal column, all the vertebrae, over 1% and over, and we lose bone. The most significant bone loss is longitudinally in our legs. So we test these little mice because I know they don't look like an astronaut, but we can learn a lot from them. We measure their little foot flops and their force, and we actually harvest the gastrocnemius, so your jumping muscle, if you will. What do we get? Well, we can see very significant 23% muscle loss in our simulations. We're suspending them on this little, I call it a moonwalker. We have them for people as well. Here it is for a mouse. And so here's our controls, the same age. Here's our controls with the same apparatus on. And then here's our data for the Mars simulation of the mouse, over 20% loss. And as I said, that's a good story. The muscular part is the best side of the story. Here's the skeletal loss. If you look at a femur, the hip bone's connected to the knee bone. That's hip, knee. That's what that bone is right there. We take slices of data through it. Only one slide on bone. We need to model bone at least look at two aspects of bone. The outer shell, that's called the cortical, outer hard bone, if you will, and the inside bone, that's the spongy bone, called the trabecular. So hard bone, inside bone. What's happening? Well, we have a choice. Here's our controller. Here's just a little cartoon of the outer bone. And our controls should be the exact same. But what's going to happen on Mars, this reduced gravity, a couple things could happen. The inside, we could lose bone. Maybe the inside got bigger. No, maybe the outside got smaller. I guess worst case, you could have both at once. So it turns out that this is what we see from the cortical, the bone loss for our space simulation. The outer diameter is decreasing. We're no longer building bone as we do right here on Earth. It's different. It's a different story to aging. That's why I go through this kind of slowly, because maybe it's the same as in aging. No, in aging, it's actually you would lose a little bit from the inner diameter, but you would have a compensatory adaptation, a little bit larger bone. The material properties don't change, even though the diameter changes. So that when you do the engineering analysis, that tells you a lot. So aging is a little different than we see in spaceflight. And here's the inside bone. So we're thinning the cortical shell about 9%. We have a significant difference in the bending moment, the bending strength of the bone. We even lose more on the inside, in the trabecular bone, the inside, but 11% thinning for this Mars simulation. Okay, so I've flown various experiments up in space. Now we're in weightlessness. It's an astronaut, Jerry Leninger, and we just fly these smart sensors, these little, just think of them as a smart scale, little force torque sensors. And since I just showed this video because now we're not bipeds, now we're not walking, we fly when you're in microgravity, and so you're kind of more of a horizontal type of person. Oh, so we develop kind of complicated models. That's a 37 degree of freedom model for an astronaut, and I have a nice little control diagram here, but then I also like to think about thought questions. Again, this is just a question for, ask a student or colleague. He's not defying physics, right? You can't do this at home. But how's he doing that? So when our colleagues were up on Shuttle, we asked him, hey, can you do these motions for us about all three axes, right? So here's Ray said, and she's actually a surgeon, So it's kind of a fun environment because you can spin. If you're on a bar stool with low friction, you can do this in 1 degree as well. And these two are veteran astronauts. This Japanese astronaut, the reason I include his motion And the secret is they're just changing their angular momentum to control their body motions. And he was a rookie flyer. It's the first time he flew, and it's the astronaut, the rookie that I've seen with the best body control ever. I mean, usually it takes veterans 30 days, shuttle missions were only a couple weeks, 30 days or repeated flights to really get, you know, to almost perform like an Olympic athlete, to be really good. And so we're interested in those things. We look at those things and we model them and analyze them. After 2 years of flying these smart sensors with the Russians in the mid-90s, 96 to 98, here's all of our data on one histogram. So if you look at the vertical axis, that's the number of astronaut motions. Landings, push-offs, kicks, boom, 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 every time they're interacting. So thousands of astronaut motions. Here on the horizontal axis, that's the force. And in newtons, for you all, for NASA, I have to put pounds down here because sometimes there's a problem with the units in the US space system. Anyhow, what does this show? It just shows you that 96% of all of our astronaut motions are under 60 newtons. Those are really low forces. Those are really low force activities. So what we did with this data, we basically proved the astronauts are not literally going to rock and roll the space station. There was a huge concern because it's true, I can exert a very large force, and that could be pretty bad for experiments or space station. But the point is I don't. When I'm adapted and in this environment, I actually, if I want to zoom to the back of this lecture hall, I push off with a digit, one finger, and I just zoom to the back. If there's a fire right now, well, if we were in space, I'm going to beat you all out of this room. And because you're all going to panic and fire, fire, and you're going to jump up, and guess what? You're going to run right into the rafters. And our job is to get out of this room if we were in space. And all I'm going to do is push with like 20 newtons, and I'm going to, so it's high precision control of very low velocity. Is, you know, after a few years of studying cosmonauts and astronauts, that's kind of what we deduced. Okay, so still a little bit on Earth here. What if we want to get rid of all this muscle bone loss? Can we do it? The data that I showed you is with astronauts and cosmonauts exercising 2 hours per day. Because we can't run the scientific control to not have the astronauts exercise because it really wouldn't be ethical. So we can't do the pure science. And you guys don't get to exercise, but you guys get to exercise. So all the data I showed you is with significant exercise, and we still have a pretty serious challenge. So we think exercise will help. It's getting better. We have better exercise equipment on space station now. Pharmaceuticals are promising. A few have flown in space, bisphosphonate, dendrite, for osteoporosis type of drugs, and maybe artificial gravity. So this is actually, but probably not Stanley Kubrick's, 2001 big flying. It's too expensive, even though engineers usually really like it. So we look at this. We look at short arm centrifugation. You all get a bed to sleep in on your Mars mission, right? This is actually Guy's design for his company when 4 people get to sleep together, and that's kind of like a bad carnival ride. You just spin around and you go 23 revolutions per minute, and you recreate your body weight, your acceleration of one body weight at your feet. So here we are in our lab at MIT. That's Rex, one of my graduate students, and he's not going to fly off. He's sleeping. I mean, graduate students are tired, but and he has a wind shade over him so that he doesn't wake up. Here's some of my undergraduates. So this is where designing and this is human-powered artificial gravity. Actually, I'm on there with one of my students because I always need to test experiments out. We didn't fly off, we were happy. We did drop the chain a lot. It's hard to get the chain, but essentially that's kind of you can pedal your way. Maybe we pedal our way to Mars.